Hey everyone, welcome! Today we're going to tackle one of the most famous, and let's be honest, most misunderstood design patterns out there, the singleton. And we're not just going to talk about it, we're going to build it the right way, the idiomatic go way. Let's jump right in. I want you to just let this sink in for a second, because it perfectly captures what's at stake here. Imagine a high-traffic system. You've got hundreds of Go routines all fired up, and they all need to talk to the database. Now what happens if every single one of them opens its own new connection? Well, your database just melts. It completely collapses under the load. And this isn't some theoretical academic problem. This is a real-world production-down catastrophe waiting to happen. The solution? You have to ensure you have exactly one connection pool. So here's our game plan. We'll start by digging into this core exactly one problem. Then we're going to walk through Go's unique way of building a singleton. After that, we'll uncover a massive concurrency trap and, of course, the right way to fix it. We'll see it all come together with a hands-on example, and then we'll wrap up with some really important do's and don'ts for your own code. All right, let's get to the heart of the matter, the singleton pattern. Really, it's all about one thing, control. It's about enforcing a super simple but incredibly powerful rule. For this one specific type, there can only be one instance of it, ever, in your entire application. And look, these examples here, they're not just nice-to-haves. In many cases, they are absolute requirements for your code to be correct. I mean, think about it, right? You absolutely need a single configuration manager to make sure everyone's using the same settings. You need one logger so you don't end up with garbled, corrupted log files. And for things like rate limiters or metrics collectors, well, having more than one completely defeats the whole point. Uncontrolled creation just leads to chaos, wasted resources, and a very unstable system. So how do we actually build this thing in Go? Well, here's our high-level blueprint. We'll start with a private struct, then a package-level variable, a public function to get it, and the absolutely crucial sync.Once for safety. Now let's build this out, piece by piece. Okay, time for our technical deep dive. We're going to start by building a really simple, naive version of the singleton. This is going to help us get a feel for the basic mechanics before we confront the biggest challenge of all, concurrency. So pillar number one is all about understanding Go's philosophy here. Unlike other languages that have static keywords, Go uses what's called package-level scope. By declaring our instance variable at the top of the package and, this is key, making our struct unexported with a lowercase s, we make it impossible for anyone outside this package to create an instance on their own. It's Go's clean, super explicit way of enforcing that only one rule. And here's the public front door, our getInstance function. Now, the logic looks pretty simple, right? The very first time anyone calls this function, our instance variable is nil. So that if condition is true, we create a new instance and we return it. Then, on every single call after that, instance is no longer nil, so we just skip the creation step and return the one that already exists. You know, this technique has a name. It's called lazy initialization, and it's awesome because we don't pay the price of creating this object when our program starts up. If a particular run of our app never actually needs the singleton, well, it's never created. No wasted memory, no wasted CPU cycles. This is a huge deal for expensive objects, like a database pool that might need to make network calls just to get set up. And this right here, leads us to the critical, million-dollar question. This code looks perfectly fine, but it's hiding a fatal flaw, especially in a concurrent language like Go. What happens if 2 or 5 or 100 Go routines all call getInstance at the exact same microsecond? And here's the big twist in our story. That simple little if instance equals nil check, the one that seems so innocent, it's about to become our worst enemy. Welcome to the concurrency trap. What we have here is a classic race condition. Just picture two Go routines hitting that function at the exact same moment. They both look at instance, and they both see that it's nil, so they both pass the check. They both create a new instance. The last one to finish just overwrites the pointer that the first one created. And boom, you've just completely shattered the core guarantee of the pattern. Your application now has two singletons, and that way lies madness.
So here's the fix. It's beautiful in its simplicity. On the left, you've got our broken, racy code, and on the right, you see the solution. Instead of that fragile if check, we wrap our initialization logic inside a call to once.do. This is the idiomatic, correct way to solve this problem in Go.
Let's talk about sync.Once because it's the hero of this story. It's this awesome little primitive from Go's standard library, and it was purpose-built for this exact scenario. It gives you a rock-solid guarantee that the function you pass to it will run exactly one time. No matter how many Go routines are hammering on it simultaneously, it runs once. And you know what the best part is? After that first initialization, any future calls are incredibly fast. We're talking about a single atomic check with zero lock contention. It's correct, it's performant, and it's simple.
Okay, enough theory. Let's actually see this thing in action with a simple but really effective example. A shared counter.
But before we even look at the code, here's a great way to think about it. A singleton is basically like the big clock in the center of town. There's only one of them. Everybody in the village looks at that same clock to know the time. You can't just go and build your own clock on your house. That would cause total confusion. The singleton provides that single, consistent source of truth.
And here it is, the final production-grade code. We've got our sync.Once variable, and our get instance function neatly wraps the creation logic in once do. Oh, and notice something really important. It returns an interface, not the concrete struct. This is a critical best practice. It decouples the caller from the implementation, which makes our code so much easier to test and maintain down the road.
All right, to wrap all this up, let's distill everything we've learned into some key hard and fast rules for using this pattern out there in the real world.
First things first, always remember that Go's approach here is special. We don't have things like private constructors or static class members. Instead, we use the power of package scope, unexported types, and package-level variables to enforce the singleton rule. It's just cleaner and way more explicit.
So, to recap the whole thing, the singleton pattern exists for one reason: to guarantee one and only one instance of a type, and to give everyone a single global way to get to it. And in Go, the safe and correct way to pull this off is with sync.Once.
But, and this is a big but, with great power comes great responsibility. The biggest knock against singletons is that they introduce global state, which can be a total nightmare for testing. For most of your components, you should really prefer passing dependencies in explicitly, a pattern called dependency injection. It just makes your code a whole lot more testable.
And that brings me to my final and most critical warning. If you ever find yourself thinking about making your user service or your order process or a singleton, just stop. Please, that is an anti-pattern. Singletons are meant for those cross-cutting infrastructure concerns, things like loggers, configuration, connection pools. They are not for your core business logic. So I'll leave you with this question to chew on. Go take a look at your own applications. What global state is hiding in there? Could it maybe benefit from the explicit control of a properly built singleton? Or should it be refactored into a dependency that gets passed in? Something to think about. Thanks for tuning in.